We have learned the basics of using malloc and free to allocate and deallocate blocks of memory. In this video, we will demonstrate using malloc and free on a nested data structure. Let's imagine that we need a nested array, an array of pointers where each element may itself point to an array. In this case, the first pointer refers to a single integer, and the second points to an array of 3 integers. While this example is small, this is a fairly common structure. We often need an array where we don't know the length or the size of the elements before runtime. Since we don't know the sizes at compile time, we have to use dynamic memory rather than statically defined arrays. First, we'll create the top-level array. We need to do this first so that we have a place to store the pointers for our subarrays. We want to create this data structure dynamically, so we use malloc to allocate the appropriate space. In our top-level array, we need enough space for 2 pointers, and each one is size of int star. Since we are creating an array where each element is int star, and we access arrays by using a pointer to the first element, we need a pointer to an int star, which is type int star star. Now we need to allocate the subarrays. We'll allocate each one individually. To allocate space for the single integer, we need to malloc one int. We assign the pointer that is returned to pointers at 0. We still haven't allocated any space for this array of 3 integers. To do that, we call malloc again, asking for enough space for 3 integers, and assign the returned address to pointers at 1. Now we have the space fully allocated, so let's set the values of some of these integers. This statement says to take the 0th element of the array of pointers, that's the first int star pointer in our array, dereference it, and set its value to 55. We could have used this array syntax to accomplish the same thing. Array syntax often feels more natural than dereferencing. Now let's modify another element. Here we look at the second element of the pointer array, and in particular the third element of the subarray. We set it to 300. At some point, we'll finish using the data structure and we will need to free the memory. You can probably see right away that we need to call free on pointers. But that's not enough. Each call to malloc needs to be freed separately. When we free pointers, we're freeing the top-level array, but we have 2 other malloc objects that need to be freed. What's worse, if we free the top-level array first, then we can't access the subarrays without using a dangling pointer. So we have to free the subarrays first. Our little data structure of 1 integer and 1 array of 3 integers wasn't terribly complicated, but it still demonstrated the need to free memory carefully. Each time you put a malloc statement into your code, you need to carefully consider when and where it is safe to deallocate the memory. If the memory is going to be used throughout the program, you may be okay without explicitly freeing the memory. It will be freed when the program terminates. However, in general, each malloc statement should have a corresponding free statement somewhere in your program. Good practice is to write the free statement at the same time as you write the malloc, so that you don't forget. In addition, as we saw in this example, you'll typically need to create data structures from the top down and to free them in the opposite order.